Is air something we take for granted? Is asthma like breathing through a thin straw? Is air quality a basic need that needs to be controlled? Is air moving across the borders and continents? The answer to all these questions is yes. Yet we only pay attention to visible pollution and disregard the invisible threat that bad air quality has on us in short and long term. International problems have to be solved with international networks, and FLAIR is one of them. Satellite monitoring, flying labs and fixed sensors are all important parts to analyze our sensitive atmosphere that protects us from a universe without any known survival conditions. Today, a ship can burn dirty fuels at sea, pollutions that eventually will find its way to the air we all share. An oil platform can dispense harmful gases without any monitoring. An industrial fire can become a threat to safety as chemicals develop deadly gases. Nature itself can provide hazards to us with eruptions and wildfires. So, how do we spot a singular emission source that can be devastating to our environment? We need a gas sensor, a sniffing dog that can fly like an eagle, detecting dangerous emissions without putting anybody at risk, and broadcast data in real time down to Earth.
I mean, people often think about dogs and gas sources because they know dogs are very good at smelling things and locating sources. And that's really how simple drone operations, the idea of putting a simple gas detector on a consumer type drone, people have a mental model of they see a high concentration, they can sort of go back like a bloodhound to the source, find the source. And that is useful. It's always useful to know who's emitting, but it doesn't tell you how much they're emitting, and it doesn't cope with real situations where there might be multiple sources, where these plumes are overlapping. You then have a much more complicated problem. You might follow back to one source, but is it the most important one? And the downside of working like a bloodhound is you miss lots of other things whose plumes you just didn't happen to interact with. So in a more technical area, if you want to solve a regional monitoring area, you have to collect data in an unbiased fashion over a large area and not act like a bloodhound. You need to note the signal but move on to new areas where you haven't measured yet because there might be something more important there. So this is called experimental design, and it's a very, very neglected area.
The challenge with most gas sensors is that they are good at one gas at a time. We need a Swiss Army knife that can perform a whole spectrum of gases, and that's where our journey begins. In Switzerland, at CSEM, a technical institute who is developing the spectrometer with a consortium of universities and commercial companies.
Well, the spectrometer is an instrument that tries to measure specific signatures that gases in the air imprint on the light that is going through the air. So what we actually do is we have a light source, we send it through the air, and we see how the air and the molecules in the air have changed the light. And the spectrometer is the instrument that detects those changes.
The biggest challenge we are facing in this project is to fit all these pieces of equipment and these optics into a shoebox.
To detect different gases, you need a source that is broad as a lamp and bright as a laser. For that, we need to go to Denmark and visit the world champions on lasers. In this case, we have a university just outside Copenhagen and a commercial developer just nearby.
many of the interesting molecules, many of the interesting pollutants that you would like to measure, they are in that regime and that is not covered by the regular sources. So our role is really to make sources that have all these colors of light that are in the important region for pollution, for FLAIR, and that we use to make for the body, for example.
But it's very bright, so it's very well focused light. And that means that it's very easy to what we call collimate it, so basically turn it into a beam that can propagate without basically losing much light over many meters. And that means you can get a long interaction length with a gas, and then you can see this gas more sensitively.
Major issue is not really to get the bandwidth, we have shown we can get that, but it's to get enough power, enough strength of the light out there. And then to make this little tiny fiber be able to last with that high power in it. To control the light in ways necessary for FLAIR, we really need to have it guided in here and have it guided with certain properties. So if you, I don't know if you can see it here. No, can you see it? Yeah. So we make a replica of the fiber. It's very big. And what we then do is we put it into a furnace. We heat it up until it starts to drop down, and then we draw it down to a fiber of the size of your hair. And you can see it's sort of a leftover of one. You can see we go from about this size down to a very small size. Now I clipped it off so it would go and become even thinner. It is actually the size of your hair, I kid you not, that is it. And if you then look at this one, imagine that this is a simple version I'm showing you, so where we only have 2 rings of holes in it. The ones we are going to use have more rings. So inside your hair we will have all these even tinier holes, and they need to be open and very, very good and nice structured for the fiber to have the properties we need it to.
As you normally find a solution to one question, you create 2 new challenges. In this case, we need a laser beam that is around 10 meters long, and to make it smaller, we need to move even more north to Sweden. Here in Delsbo, we can find a shoehorn that will fit a long laser into a shoebox. It's called a multipass cell.
A multipass cell is just a cavity where light bounces back and forth multiple times.
And the challenge is to do that in a efficient way so that it can be housed in a shoebox and yet be low cost enough. We are not allowed to use very expensive mirrors and stuff. We have to find alternative ways to manage this.
I have designed the beam to go around 32 times back and forth. So, and the distance between the 2 mirrors is 30 centimeters.
Difficult challenge for this project is to have a tolerance setups for the unit and to calibrate each mirror in right position and have a stable situation for it. Right now it's just a rough model, but it's going to be a much rigid model later on.
So, we created a beam, bounced it around like a ping pong ball, divided it into different spectra. Now, what will reveal those nasty little molecules that are flying around? So, let's go to Spain. Here, we can find the camera that will do just that. See the invisible.
The camera is one subsystem of the spectrometer. Spectrometer basically has a light source, which is a supercontinuum. Also has some optics for separating the different wavelengths, and also the sensor for detecting the different colors.
So you are the sensor?
We are the sensor of the spectrometer. I think the visible part of the electromagnetic spectrum is very narrow. It's only for 0.4 to 0.7 microns, but the huge information in the left side and the right side.
I think the biggest misconception of all work related to measuring gases is that measuring concentration tells you something important. It doesn't. Concentration is the consequence of a gas release. If you think about it, any release of gas goes from 100% to 0%. A concentration measurement doesn't tell you anything about how big or important or significant that release is, let alone where it is or what the mass emission rate is. You need a collection of concentration measurements and an understanding of how gas dilutes and spreads in the wind to be able to infer the location of the source. And although everyone talks about concentration, what people are really interested in is who's emitting how much. And that's a different problem. That's an inverse problem which is very complicated and requires a very specific approach to get it right. It's extremely difficult to solve.
We have a technical setup. We could call it the hardware. The soft part is to know what to look for and how to do it. Time to travel up north to Holland and Radboud University. Here they work on what gases to look for in different spectra.
If you compare what we detect gases compared to, for example, looking through with the sun through a stained window, they see in the stained window, you see some parts of the stained window are red glass or blue glass or green glass. And so you can distinguish the red glass from the blue glass. So the red is coming through, that means that the blue is absorbed. And this way you also detect the gases. I mean, the laser is has a very broad range of wavelengths. And some parts of the light are absorbed by the gas, other parts of the light are not absorbed, other waves are not absorbed. So we can distinguish the red from the blue, stain, red, so one gas from the other gas.
How it works? Well, we have a superconductor laser, which contains a lot of color components. And then this superconductor laser is sent through a scanning grating, and the scanning grating diffracts the beam in different positions. And then we send the beam into a multiple cell and use the multiple cell to enhance the optical path length. The higher the optical path length, the higher the signal. So that can boost our sensitivity to even ppb levels of the gas concentration.
So what we do is we look at the spectroscopic behavior. So we're looking at the behavior of the gases, where they absorb, how they absorb, where to measure with the laser, how strong the gases are absorbing, which other gases are competing with each other, which gases are competing with each other in the absorption. So to know indeed, if you want to measure methane, that we really measure the methane.
I think this is not working, the green. I think the Vigo is off. No, that's just I was moving. You shouldn't get this. No. No. Yeah. Stop. We'll have to bring this to channel 0. Yes. Now it comes. Okay, now it's back. Problem solved. Okay.
It's a high-risk project for sure. Now, you need also to process the data, and that takes us right back to Switzerland again. Here at EMPA they know how to process incoming gas levels and make sense of it. But not only that, as you might encounter a sinner that spewed out toxic gases, there will be a demand on references that there were no such gases elsewhere nearby.
We do two things. We provide reference measurements to trust in the absolute values, but we also provide models that make this link between the measurements and the source strength and source location. That's exactly our goal and aim. Air quality measurements started out with fixed locations 40, 50 years ago, in the case of CO2, even a little longer. We are now learning more and more about what the distribution of those pollutants are, and since this distribution is very complicated, you need measures to actually determine it. And one of the ways to do this is by going to the exact place, and you cannot do this by actually moving a large measurement station, but you can do so by flying a small instrument that measures many parameters at the same time. And this approach as such is something that will gain tremendous importance in the future as sensing technology will advance, and as flying technology, think of drones, will also advance in the next few years.
We are at the end of June in 2018, and there are still obstacles to overcome. But here, in this meeting, all the brains that cooperate around this challenging task are gathered in Zurich. Will the dog take off like an eagle?
So this is why they're using a longer range drone, not one of these sort of toys that goes no more than a kilometre by regulations, but one that can cover hundreds of kilometres and be controlled remotely, and fly a more sophisticated sort of detector that can measure several species of interest. And that's the real technical challenge of the project. It's a very difficult thing to do. It's a highly innovative project, and it's a really good consortium. There's a good spread and overlap of skills. It's one of the most effective consortia I've ever seen.
Absorbent basically means it's just 100% absorption.
Because then you guys will have several different versions of the DOW and we'll have some interference from the water as well. As you see, this is a huge water line and this is the tail of it.
The first image will be here, and the second there. It will go like this.
Then they have not managed to make something that small, so to do it straight away with a mid-R is quite challenging.
It's validated outside the lab or something, I don't remember the exact wording, but
if the temperature is no cold,
so it's really a box, a square box.
The elements and
A European Union at its best, working for a better environment across invisible borders.
And quite light.
Oh, did we forget one thing? The unmanned aerial vehicle that will take all this technology to the site. Time to move again. This time we will go to Portugal. Here we will find devoted engineers that love to make things that can fly unmanned.
Well, essentially you have a lot of technology inside. So you're basically replacing the human with a bunch of computers, which need to do exactly the same as the human does when he or she is driving a car or flying an aircraft.
The biggest technical challenge is, of course, making the sensor compact enough to be compliant with the constraints that we have in terms of payload on the UAVs.
Putting this sensor inside a larger aircraft will allow us to show that it's actually feasible to measure air pollution using a drone. Why use a drone and not a regular manned aircraft? Because usually drones are cheaper to operate because they don't have the pilot. They cost less to fly. They also allow you to fly in areas where usually you wouldn't fly with a pilot because they're too dangerous. So for example, if you want to monitor what a volcano is throwing out during an eruption, you wouldn't fly a manned aircraft over the volcano, but you might be willing to accept the risk of flying a drone over the volcano. So that's one of the reasons why it's appealing to use a drone or install this type of sensor on a drone instead of a manned aircraft.
Will our kids breathe clean air? Will we take fresh air for granted again? With the dog and the eagle, we might come a step closer to that.